In this lesson, we're going to continue on with combinations. Specifically, we're going to look at a few different problem-solving strategies, which isn't to say that you haven't used problem-solving strategies before, but here's a few different ones that we haven't taken a look at quite yet. Before I get to this first one, a lot of students look at this and think that it's a formula or some sort of equation that they're supposed to use, and it is not. It's just a simple logic process that you may have to modify depending on the type of question that you have. So rather than think of that as something you plug numbers into, I want you to use it to think about how to approach a problem. So for our first example, we're going to look at a bag of candy containing some different colored gumballs in it. And we're going to look at choosing, and then this is the key word here, some of the gumballs. Now, we don't necessarily know whether we're going to choose 2 or 3 or 5 or all of them, but we're going to choose some gumballs. Now, again, depending on the situation, we may or may not consider 0 gumballs to be some of them. I will not usually consider the word some to mean nothing. Some means at least one. And in this question, it's pretty specific. A child gets into the bag and eats at least one of the gumballs. So we have 3 red, 2 blue, and 4 yellow gumballs. Here's the question. How many ways could they have eaten some of them, or at least one in this case? So for our logic, the way that we're going to kind of think about this one is to say, okay, um, let's look at each of the colors individually, or each of the things. In this case, happens to be colored gumballs. So the kid looks at the red gumballs and says, how many different ways could I eat the red gumballs? Well, if there's 3 red gumballs, they could eat none of them, or one of them, or 2 of them, or 3 of them. So there's 4 possible ways. And just for now, for this question, I'm going to write out that 4 as 3 plus 1. And the reason I'm doing that is to make sure you understand the logic of there are 3 gumballs, so 1, 2, or 3 are options, but so is none. I could choose no red gumballs. So that's where that plus 1 comes in. Now when it comes to the blue gumballs, you could choose 1 or 2 or none of them. So there's 3 options, but I'll write that as 2 plus 1. And the 4 yellow gumballs, I could choose 1, 2, 3, 4 or none. So that's going to be 4 plus 1 options. Now that almost answers the question, except for the fact that the kid could have gone up and said, okay, I'm going to choose no red and no blue and no yellow. And that doesn't actually meet the criteria of our question. So we're going to subtract 1 off the end, which gets rid of the case where they chose none, none, and none. So the minus 1 on the end gets rid of the scenario with no gumballs chosen. Once we have that, then this just becomes 4 times 3 times 5 minus 1, which is 60 minus 1, or 59. So there are 59 possible ways that they could eat at least one of the gumballs. You'll note that the equation that we use looks very similar to the logic I put up there. It's not, well, in this case it's identical, but that's because our situation happened to work out that way. We have to modify that logic anytime the question is slightly different. And I'm not going to try and make each of these into their own scenarios. Again, these are just logic problems. So what if the child took at least 2 gumballs? Okay, fair enough. That's going to look a lot like the first one. They can still choose 0, 1, 2, or 3 red. I'm just going to jump to the 4 on that one this time. They can choose 0, 1, or 2 blue. That's 3 options. And they can choose 0, 1, 2, 3, or 4 yellow. That's 5 options. What's different now is that they're not allowed to take no gumballs, but they're also not allowed to take 1 gumball. Well, there's only one way to take 0 gumballs. So that's so far exactly what we had for part A. But now we have to subtract off the number of ways that they could take 2 gumballs, because we're not allowed to have, or sorry, number of ways they could take 1 gumball, because that's not an option this time either. Well, the number of ways of taking 1 gumball is going to be 3, because that 1 gumball could either be red or blue or yellow. So we're going to subtract off an additional 3 there. So that's the number of ways of selecting no gumballs or 1 gumball and taking it off of the total. So we get an answer pretty close to our 59. It's just going to be 3 less, or 56. All right, modifying the logic just a little bit more. What if the child took at least 2 of each color of gumball? Okay, so let's just think about it. There are 3 red gumballs. They have to take at least 2. That means that they could take 2 red or 3 red. That leaves us with 2 options. Then they get to the blue gumballs. There's 2 blue gumballs. They must take at least 2. There's only one choice they have there. They have to take both of them. For the yellow gumballs, they can take 2, 3, or 4. That gives them 3 options. And in this case, we don't have to subtract off anything because it's impossible for them to take less than 2 of each, given that we've set it up to be this way. So there is no scenario where they don't take any gumballs. There can't be. They took 2 of each. Um, so we don't have anything to subtract off this time, and the answer just turns out to be 6. Okay, now it looks like I broke the pattern on these about at least 1 gumball, at least 2 gumballs, and now we're getting to at least 3, but I put that other one in the middle. It's because the 3 gumballs is actually a little bit more challenging than the other. Okay, so here's the way to think about it. We have, oh, I should just make a little note here. We have 3 red, 2 blue, 4 yellow. 3 red, 2 blue, 4 yellow. If we want to choose at least 3 gumballs, then we can actually set it up much like we set up the first couple. There are 4 ways to choose red, 1, 2, 3, or none. There are 3 ways to choose blue, 1, 2, or none. 5 ways to choose yellow, 1, 2, 3, 4, or none. But now we have to subtract off the scenario where we have no gumballs taken. Well, there was just one of those. The scenarios where we take 1 gumball, there are 3 of those. So this is so far exactly identical to part B. Now here's the tricky part. How many ways could the child have taken 2 of the gumballs? Okay, now this is where you're going to actually have to think about this logically for a moment. If they've taken exactly 2 gumballs, I'm going to break it down into 2 kind of categories. One category, they've taken 2 of the same color. The other category is they've taken 2 different colors. If they've taken 2 of the same colors, that can happen 3 ways. They could either take 2 reds, 2 blues, or 2 yellows. So I'm going to subtract off 3 more cases. If they have 2 different colors, now this one's small enough that we can do it manually, but if they take 2 different colors, they could take a red and a blue, a red and a yellow, or a blue and a yellow. That's 3 possible ways. So I'm going to subtract another 3. However, I do want to point out that this part here, that last 3, could actually be thought of as 3 choose 2, which happens to equal 3. Because of the 3 colors, the child is choosing 2 different colors to do. And this part right here actually could be thought of as 3 choose 1, because I have 3 colors and I'm choosing 1 color to take 2 gumballs from. So despite the fact that we can work this one manually, I think you can see how you might be able to expand it up to larger scenarios if we had like 8 different colors of gumballs and we were taking different numbers off. I will say that these questions become very complex very fast if there are too many things, um, too many colors, or too many different scenarios. So we're not going to go much further than what we just did, but I did want to show you where that number came from. Okay, so that said, this becomes 60 minus a total of 10. So there would be 50 possible ways that the child could take at least 3 gumballs. Okay. Now this you may have done in other classes, not necessarily the way I'm about to approach it, but you may have talked about prime factorizations before. And a prime factorization is where you take a number and you break it down into a multiple of all of its primes. Now just a reminder off to the side here for primes. A prime number is any number divisible by 1 and itself, and it has to be 2 unique numbers. So I often have people, including other math teachers, who have argued that 1 is prime because it's divisible by 1 in itself, but the definition actually is that they have to be two unique numbers. So 1 is not prime. 2 is prime because it's only divisible by 1 and 2. 3 is prime because it's only divisible by 1 and 3. 5 is prime because it's only divisible by 1 and 5. 7, etc. Now, obviously, no even number other than 2 will ever be prime because every even number bigger than 2 is also divisible by 2, 1, 2, and itself. Um, not all odd numbers, obviously, are prime similarly. For instance, 9 is not prime because it's divisible by 1, 3, and 9. So the next prime number is 11, and then 13 and 15. Sorry, not 15, 17, because 15 is divisible by 3 and 5. Okay, so those are prime numbers. Now it works out nicely because if you're trying to write out a number as a list of primes multiplied together, if one was a prime, you'd be listing it an infinite number of times because you could keep multiplying it by 1 over and over again. So what we're going to do for this question is see if we can figure out what the prime factorization of 600 is, and then how many factors 600 has. And I realize this seems like a very different question than what we've just done, but when we're approaching it, I think you'll see it's actually the same as the Gumballs question. Okay, first part. We want to figure out the prime factorization of 600. So there's a couple of ways that you can do this. One of them is faster, shorter, but takes a little bit more mental math. The other one is more foolproof, but takes a little bit more room and a little bit more time to do. So I'm going to do it both ways. The first method, I want you to think about it this way. 600 is equal to something times something. Now I could pick any two numbers I want, but I'm going to try and pull out the smallest prime I can just because it makes life easier. So I'm going to say it's equal to 2 times 300, but I'm not going to write the 300 down. I'm going to keep track of it in my head. 300. 300 is equal to 2 times 150. Not writing down the 150, just keep it in my head. 150 is 2 times 75. 75 is, I can't divide it by 2 anymore, but I can divide 75 by 3, which is 25. 3 times 25. And 25 is now divisible by 5, and that's 5 and 5. Now, the beauty of this is even if you do lose track or you mess up a little bit, you can always double check at the end that this is correct by multiplying it out again and seeing that you actually get the original. So these are easy to double check. 2 times 2 is 4, times 2 is 8, times 3 is 24, times 5 is 120, times 5 is 600. Done. Now, if you're someone who has a hard time keeping track of numbers in your head, you can do it in this way. It looks kind of like a tree diagram, except instead of showing possible outcomes, it's just showing possible ways of breaking down the numbers. And I'm going to purposely choose weird ones here instead of doing the prime numbers right off the bat, partially because it makes the diagram a little bit nicer and partially showing it doesn't matter which numbers you choose. So I'm going to say 600 could be written as 20 times 30. And then I'm going to say 20 could be written as 4 times 5, and 30 could be written as 5 times 6. And then here, 4 can be written as 2 times 2. The 5 is a dead end because it's already prime. The second 5, same argument. And the 6 can be written as 2 times 3. So now if I look at that tree diagram and I list everything in order, smallest to lowest, I have to look at the bottom of each branch. I can't look in the middle, so I have a 2, a 2, and a 2. I have a 3, and I have 2 5s. So I now just write them out and get the exact same thing I did the first method I used. Whichever method you'd like to use of these is fine. Just please, regardless of which method you use, double check it before you continue, because if this part is wrong, everything you do from there will be wrong. And I will say that normally on tests and stuff, if you make a mechanical error somewhere, I'm usually try to be very forgiving. On this question, if you screw up the first part and carry it through and bypass a whole bunch of the things, the questions I'm trying to ask or the ideas I'm trying to pull out, I will not give you marks because this one's so easy to check and I'm telling you to double check it. So do not screw up the first prime factorization, and the rest should be pretty easy. Okay, I'm just going to erase those little tick marks for a second, just so that I can make different tick marks underneath. And I'm going to do these ones in red as well, actually. What I want to point out is that the 2's, there's 3 of them. The 3, there's only 1 of, and the 5, there's 2 of. So our question is, how many factors are there of 600 other than 1? So we're not going to consider 1 to be a factor. It is, but for our purposes right now, the question's saying don't consider it a factor. And so for instance, 600 has lots of factors. So 600, just as an example, let me just write this over at the side. Example, 600 has a factor of 100. Well, 100 is really 2 times 2 times 5 times 5, right? 100 is 10 times 10, 10 is 2 times 5, so 2 times 2 times 5 times 5. So really all that is a subset of the prime factors. I'm taking 2 of the 2's and 2 of the 5's. I'm not taking the third 2 or the 3. So I'm just choosing some of those. So the way that I approach this is to say that the number of factors means that I could take any number of 2's, 1, 2, 3, or none of them. So 2's, 3's, and 5's. What makes this different than the gumball question is the fact that I'm counting number of numbers instead of number of colors. And that usually confuses people because they're losing track of whether I'm talking about 2 or the number of 5's, which is 2. So anyway, when it comes to 2's, there are 4 options. Again, I can choose 1, 2, 3, or none of them. When it comes to 3's, I can choose one of them or not, well, one of it, because there's only one, or none of the 3's, which is, yeah. So there's 2 options there. And the 5's, since there's 2 5's, I could choose 1, 2, or none. That's 3 options. And I'm going to subtract off 1, which is the scenario where my factor has no 2's, no 3's, and no 5's, because that would just be a factor of 1, which is not allowed. Now that I've done that, this is just like the gumball question. So I have 4 times 2 times 3 is 24, minus 1 is 23. So that means that 600 should have 23 factors other than 1. If you want to try to list them, you can. That would be 2, 3, 4, 5, 6, 8, 10, 12, 15, 18, nope, not 18, 20, and so on. I'm not going to try and get through all of them because chances are I'm going to miss one anyway. But there should be 23 of them when you're all said and done. So for part C, we're now asking how many of the factors are prime. This again is just kind of looking at restrictions and thinking about the logic. Well, how many prime factors are there of this? And the answer is there's just 3. 2, 3, and 5 are the 3 prime factors. How many of the factors are divisible by 5? So again, going back to kind of the list I partially made, 5 was divisible by 5, so was 10 and 15 and 20 and so on. So a bunch of them are divisible by 5. But what does that mean in context of our question? Like, how does that relate back to the numbers we got? Well, this is no different than saying we have to have at least one yellow gumball. Except in this case, what we're saying is we have to have at least one 5. If there is no factor of 5 in it, it won't be divisible by 5. So we've got the 3 2's, which we can do again in 4 ways. We could choose 1, 2, 3, or none of them. The 3's, we could choose or not choose the one that's there, doesn't matter. But for 5's, we can no longer choose no 5's. Choosing no 5's means our answer won't be divisible by 5. So with 2 of those, we can choose either 1 or 2, but not none. So we only have 2 options now. Now, unlike part B, where we subtracted 1 at the end, which was basically the case where we chose none of the 2s, 3s, or 5s, we don't have to subtract it this time because we guaranteed that we have at least a factor of 5. So we don't have to subtract off because there is no case where we've chosen nothing. So now 4 times 2 times 2 is 16, which means 16 of those factors will be divisible by 5. Lastly, for this question, how many of the factors are divisible by 6? I will point out that I have on tests before had people say, well, there are no factors divisible by 6 because 6 is not in our prime factorization list. It's true because it's not prime. It is, however, equal to 2 times 3. So if it's divisible by 6, it must be divisible by both 2 and 3, which means that when we're selecting 2s and 3s, we have to have at least one of each of those. So for the 2s, we had 3 2s, which means we have to choose 1, 2, or 3 of them. So we have 3 options. No 2s is not an option. For 3s, no 3 is not an option, so we must choose the 3. And for 5s, we can choose 1, 2, or neither of them, so that's 3 of them. And that gives us a total of 9 possible options, or 9 factors that are divisible by 6. Now, again, you'll notice there was no -1 at the end because you can't have a case where you've selected nothing if we've guaranteed a 2 and a 3 are there. So despite the fact that this factorization problem looks drastically different than the Gumball problem, you'll realize that the math and the logic behind them are pretty much the same. Part D is essentially the same thing as you have to have at least one yellow gumball, and part E is essentially the same as you have to have at least one red and one blue. Same idea. Okay, this last one is actually a fairly short idea, but it's a very powerful one for solving questions. And it's the idea that the number of subsets that we can make is always going to be 2 to the n if we have n distinct objects. So let me explain why that's true, because I don't need to write that for you to use this logic before. So in our example, we've got 18 contestants auditioning for the hit show So You Think You Can Yodel, a Swiss version of So You Think You Can Sing or Dance or whatever. Judges can accept as many or as few of the individuals as they wish. So they could choose none, they could choose all 18. They're just basing it completely on talent and yodeling ability, apparently. By the way, if you don't know what yodeling is, just look it up. I don't know if I'd recommend looking up a video, but look up the definition. How many different combinations of people could they choose to accept into the show? So here's the way I want you to think about it. We can approach this actually in a very long, tedious way, which is of the 18, they could select 0, or of 18, they could select 1, or of 18, they could choose 2, or choose 3, or choose 4, up to 18. That's going to give 19 possible cases, which is very tedious. I want you to think about how you do this if you were the judge. What happens when that first person comes up on stage? You're going to either accept them into the show or you're not. There's 2 possibilities. So the first person, there's 2 possible outcomes. You either accept them or you don't, which is a little bit like the gumballs. If there's one purple gumball, you either eat it or you don't. The second person, 2 possible outcomes. The third person, 2 possible outcomes. Accept them or don't. And then this is going to keep going until we get to the 18th person. And there's 2 possible outcomes for them as well. So when all is said and done, we have 2 choices for each of the 18 people. That's 2 times 2 times 2, 18 times, which is 2 to the 18. And that's good enough for understanding why the equation works, or why the logic works. But just for the heck of it, 2 to the 18 is 262,144. So there's that number of ways of doing it. And again, this logic of choose to include or not include each individual object is going to come in handy later. Now, I specifically used set words and subset those things that we learned about at the beginning of the unit, to remind you that a subset of 18 things is any number of those things up to 18 or right down to 0. And then it gets a little bit more complicated. Like if there's 9 of the 18 accepted, which 9 are they? And then you would just say, okay, well, if there's exactly 9, it would be 18 choose 9 people. If there's exactly 5, it's 18 choose 5 people. And if it's all of them, you have to add up all those 18 choose 0 plus 18 choose 1 plus 18 choose 3 all the way up to 18 choose 18. And we are going to come back a little bit later in the unit and re-explore that idea in another application. But for now, we're going to leave it at that. A subset has a set has 2 to the n possible subsets. All right, those are some problem solving skills. Again, the questions seem to look very different, but this is really the gumball question where it's just 18 different colored gumballs and you can accept or not accept each. In this case, we were allowed to have 0 contestants show up or be accepted, so we didn't have to subtract 1 at the end. I'm going to stop there. I'm going to let you try some problems and let me know if I can help in any way, shape, or form. We'll see you next time.